Hello, I'm Truman Roland, and this is my paper, Supercritical Fluid Processing of Food and Biomaterials. So basically, my paper is about using supercritical CO2, which is carbon dioxide at a very high pressure and temperature, which has properties of both a gas in that it will fuse through a solid, and like a liquid in that it will solvate and transfer nonpolar materials within that solvent. So for instance, oil is a very common one. So what you can do is basically get a biomaterial of any variety. Often this will be like a plant or something with an oil or something that we wish to obtain from inside. And we can then run our liquid CO2 through it, and it will pick up this oil, and then we can use various mechanical techniques to physically separate it and get a desired product as shown in the diagram on the right. So basically, we have our initial equations on the left. The top two on the left are ones that describe M, the rate of mass transfer in kilograms, for both the from the oil, from the biomaterial to the solvent, and from the solvent into the collecting pan. Now for this paper, they chose the example of ginger and ginger oil. Basically what they did is they dried out some ginger, they ground it up, and then they used supercritical CO2 to extract the ginger oil from inside. So we have K, a mass transfer coefficient, then we have A, the surface area of the particle, so that a larger surface area will be conducive to more exchange of the oil. And then we also have the concentration from for the particle to the solvent, Cg, that will be important later on, and then to the collecting pan. Now we can put these equations together if we combine the mass transfer coefficient into one, adding the sum of the reciprocals equals the reciprocal of the overall transfer coefficient. And we can rearrange these such that we get dC over dt, basically the rate of change of the concentration of oil within the ginger particle, equals a constant related to the surface area, equals the concentration of the mass of the oil in the particle versus that in the CO2. And so basically this model will tell us what the concentration of the oil is within the particle, so it should go down over time. So this is a first order differential equation, so we can solve it by separation of variables, and we get an exponential decay function with a steady state condition or ultimate condition of Cg, basically concentration of the oil in the gaseous CO2 phase. Now this model is mostly predictive for the sort of mid portion of the extraction, not the beginning where the concentration in the gaseous phase is rapidly increasing, and not towards the ends where it might be falling off, but more towards the middle. And so this is the block diagram we use to solve this differential equation. It's a first order, so we only require one integrator. And so here we can have the first, typical conditions of a particle of 0.111 millimeters. And we plug in the information provided by the paper, and we see that it predicts it fits the predicted exponential decay model, and that after an hour, about 27% of the oil is eluted for a typical particle size. Now the paper also experimented with a slightly larger size of 0.184 millimeters, and they found that this slightly decreased K, the transfer coefficient, from 28 to 26 times 10 to the negative 8th. And so we can see that with a slightly larger particle and a slightly lower diffusion coefficient, that after about an hour, about 25% of the oil is eluted. Now this isn't very significant, this isn't very substantial, but it is significant. As we'll see, as if we linearly extrapolate from those two data points, if we have a millimeter diameter particle, that this will actually reduce the transfer coefficient as well as the percent oil eluted after an hour by an entire order of magnitude. And we see that with a much larger particle, which would ultimately result in less surface area, that we have a much slower diffusion that's more linear rather than the exponential decrease initially seen. And we can also look at an oil-rich particle in which there's a greater difference between the solvent and the concentration in the particle, so that this causes a greater driving force, which causes the relative portion of the oil in the particle to be eluted out after a certain period of time. So in this case, it's 36% after an hour, as opposed to the initial of 27. So in conclusion, this model shows an exponential decay that's similar to the heat example we used about the heated beads being dropped into a bath. We know that this is physically accurate as it ultimately approaches the concentration in the gaseous phase, which we know would be the case as they would then be in equilibrium, and we know that processes cease to continue after they equilibrate. And so some practical considerations for this model is to use a large volume of supercritical solvent as to make sure that the concentration in the gaseous solvent is relatively stable such that it is constant, and this will keep the model accurate. And to make best use, practical use of the model, we should switch out the particles when they begin to approach the asymptotic limit to basically keep our operations around the most dramatic decrease in the oil concentration given by the exponential model. And here are my sources. Thank you for your time.